Okay, so hello and welcome to this video tutorial for Engineering Mechanics Statics by R.C. Hibbeler. So we have this problem from chapter 2, which is asking determine the resultant force at A, where we have two forces, FB and FC, acting on point A here. And the forces FB and FC are also in line with some position vectors. So FB, for example, is in line with this position vector AB, and FC is in line with this position vector AC. This problem is very similar to the previous problem in the chapter F2-23, which I've solved in a previous video. If F2-24 has come at you and it's completely new and you have no idea what's going on, I might suggest to you having a look at my video for F2-23 and picking up on some of the concepts that we deal with there. For F2-24 here, just to kind of avoid repeating myself, I'm going to emphasize and suggest to you how you might generalize for a problem like this. Generalization or generalizing problems is a very important idea and a very important skill for mathematicians and engineers, since it enables us to deal with similar problems while reducing the labor time or reducing the length of the process of having to do them. So I'm going to kind of emphasize to you guys how you might generalize to solve this problem. To suggest how you might generalize solving this problem, I'm going to kind of focus in on how you might solve for the x component of FB here, because the process for finding the x component of FB is going to be very similar to finding that of the y component for FB, the z component, or the x, y, or z component of FC. It's a very similar process, right? So it might make sense to generalize it. Let's go ahead and solve for f of x then. Let's just kind of let's just solve it. So we could start off by determining the alpha angle here. So we can say the cos of alpha, let's call it alpha b since it's in line with force B, is equal to ABX over AB. Therefore, alpha B is equal to the inverse cos of ABX minus 2 over AB, which is 6 in this instance. Okay, we effectively have a value for alpha now. We can then kind of reuse that. So we might take this equation, this formula in the bottom left here, and use it to solve for f of x. Let's rearrange it for f of x. So we can say f of x here is equal to f cos of alpha, which is equal to I should write x comma b f b cos of alpha b is equal to, in this case, 600 times, to write this out fully, the cos of the inverse cos of minus 2 over 6. But we understand, if you've watched my video for F2-23, that these cos's, they cancel, right? They cancel out. So we're just left with this minus 2 over 6. And minus 2 over 6 is kind of representative of this ABX over AB idea. So how might we kind of go ahead and generalize then? Well, we might say that using this idea that the x component is equal to its magnitude, let's just call it f, times the kind of x component of the position vector that's in line with over the magnitude of the position vector that's in line with. So we can take this and use this almost as like a general form. So we can easily solve for x comma b here. We can describe it as minus 2/6 of 600, which is minus 200. We can use the exact same idea for the y component of b. We can say, using this general form that we've kind of derived here, that this b component, this y component of b is equal to, well, it's going to be the y component of AB over AB, if that makes sense. So the y component here is 4. The denominator here is 6, which is nice and convenient because it gives us a value of 400, which we can solve for in our head. Fz comma b is going to be 600 times minus 4 over 6, which again is minus 400. Let's do the same for the force C here. Where shall I write it? Let's just write it below. F x comma C, that's going to be 490 times the x component of that position vector, so minus 6, over the magnitude, so 7. Again, I can do this by inspection. That's going to be minus 420. Fy comma c is going to give 490 times 3 over 7, which gives me a value of 3 times 7, 210. And fz comma c is going to be 490 times minus 2 over 7, which is going to be minus 140. Oops. Okay, so we've got the x, y, and z components of forces C and B here, and we've done this in a way that was much quicker than as we might have done it for F2-23. If you look back on F2-23 here, we wrote out quite a lot more. This idea here, we haven't had to really kind of write out. This idea we're about to write out here, aren't we? So determine the resultant force at A. Let's write it out in Cartesian form. So we could say then the resultant force here, let's call it Fr, is going to be equal to, well, its x component or its I component is going to be minus 200 plus minus 420, so that's going to be minus 620. I, its j component, 400 plus 210. It's going to be 610. J. And its z component is going to be minus 400 plus minus 140, which is going to be minus 540 k. Okay, the question's a little bit vague. It says determine the resultant force at A. We've given it in its Cartesian form. Let's, for the sake of it, just give it its magnitude as well here. So that is going to take a value of the square root of 620 squared plus 610 squared plus 540 squared, which when we bung in our calculator takes a value of 1,067 pounds. Okay. Looks like we, oh hello, let me draw. Okay, looks like we have our solutions to our problem here. If you have any questions or comments about that problem, please feel free to leave them down in the comment section below. Otherwise, thank you very much for watching.